For these following functions, we're going to compose both ways and simplify the statements down. So f of g of x is going to be f of x, which is going to be x plus 2, but g of x is going to get plugged into there, so x minus 2 plus 2. That just gives us this, and we get x. G of f of x, g of x is going to be x minus 2. F of x is x plus 2, so that's going to get plugged in for x. That's just x plus 2 minus 2, which gives us just x. Okay, f of g of x. F of x is 7 times x, which is now going to be g of x. The 7's cancel, and we get just x. G of f of x. G is x over 7. Of course, f of x is 7x. 7's cancel, and we get x. Finally, f of g of x here is going to be f of x is x to the 5th power, and then we plug in the 5th root of x into there. Of course, the 5th power and the 5th root cancel, and we get x. G of f of x equals the 5th root of x, but now x is now x to the 5th, which is f of x. Those cancel, and we get x as a result. These are what signify inverse functions. When you compose them both ways, you get x as a result. What this means is that no matter which way you plug it in, if you plug x into two inverse functions that are composed, you will always get x out as a result. And it has to be just x. It can't be like absolute value of x or anything like that. It has to be just x as a result. Give it a try in number 2. Now, these are the graphs. We have f of x is in red and g of x is in blue. And the line y equals x is this black line. So this one here is x plus 2. This one here is x minus 2, just what I had written up above. This one here is 7x. This one here is x over 7. Then we have x to the 5th power and the 5th root of x. And the question is, do you notice a relationship between all of these things? Well, hopefully you can see it, but if we reflect this line across the y equal x line, you can see we get the exact same thing. So the blue line is a reflection across the y equals x line. The same thing is true here. Reflected across this line. This point goes up to here. It's just reflection. This point goes down to here. This spot goes over to this spot. This one to this one. You know, across the line, just like that. It's just a reflection across the line. That's what an inverse function does, is it always reflects across the y equal to x line, which is the identity line, or the parent function of a linear function. And that's because inverses undo the operation. So y equal to x is a natural thing because that's where you're changing x and y. Now, I'm going to draw the inverse for this function here. All I have to do is draw the y equal x line that goes straight through the origin, diagonal. I'm just trying to hit all those grid lines, make a straight diagonal line. And the inverse of this function is going to be reflected across this line. So it goes over to 2, then it's going to go down to 2. It goes from -4 up to 2. It's going to go down to -4 over to 2. And it looks like it does this. So that's the inverse function there. Okay, same line, y equal to x. All right, this one looks like it asymptotes downwards at the this y-axis. That means if I flip it across, it's going to asymptote to the x-axis. It crosses here at, say, 1, 2, 3, 4. So 1, 2, 3, 4 is where it's going to cross there. And then this point, it looks like it crosses. That's going to be at over 3 down, no, over 2 down 1, up 2 over 1. This point's over 1 down 2, up 1 down 2, something like that. Looks something to that effect. You can see that I've just reflected these points across the line here and got an estimation for that. Try it out for yourself in number 3. Now, this is the graph of x squared. And the question is, what would the inverse graph look like? Well, if we graph this thing, the inverse is going to look something like this. And go down like this, something like that. And what is the problem with this inverse graph? Well, the main problem is that it does not pass the vertical line test. So this is not a function, and we want to work with functions. So it's not a function. Now, we could assume that the square root of x is the inverse of f of x, which is x squared. And that's what you would naturally assume, or naturally want it to be. The inverse of x squared should be the square root of x. And the question is, does this satisfy the definition of inverses? Well, all we have to do that is compose them both ways. So f of x, I should say f of g of x, equals the absolute value of x squared. And this gives us x. And then g of f of x is x squared. And then I should do this, the square root of x. And this is where the issue comes in, is because when we do this, we do not get x as a result, but instead the absolute value of x. That's because everything that's underneath the square root, everything here is being squared. And when we take a square root of it, it'll always give you the positive answer for this. But that's not true if we want to have full inverses, right? The square root of x squared should just give you x, but it will only ever give you the positive result. If you were to graph the absolute value of x, or sorry, the g of x here, the square root of x, you're going to only get this portion of the line. And that's the reason why you'll see whenever you solve equations that have a square in them and you want to take a square root, you have to add a plus or minus in front of it. That minus is what gives you this bottom portion of the line. If you don't have that, then you take this whole square root, and you'll end up with the absolute value of x. And this does not satisfy the definition of inverses. So no, it does not satisfy the definition of inverse. It does, however, I should say, it does when x is greater than or equal to 0. And that's the important distinction here, is that when x's are positive, you will always get the inverse. They are one-to-one inverses. And that's going to be just this top portion and just this portion here. If you just kind of like exclude all that stuff and all that stuff, then you would actually get inverse functions. But that's a limiting behavior, or where you're limiting the behavior of the graph to do that. Now, a function is one-to-one, has an inverse, or also called invertible, if it passes the horizontal line test. And that you can see, if we go up here, we take a horizontal line, it crosses it twice. So no, this does not pass the horizontal line test. Very similar to the vertical line test, except now we're looking at a horizontal one. If it doesn't pass the horizontal line test, if you flip it across the y equal to x line, then you're going to get a relation that is somewhat an inverse of the graph you had, but it is not a function. And that's what I just showed here. If it doesn't pass the horizontal line test, the questionable inverse will not pass the vertical line test. All right, give it a try in number 4.